right now, as you listen to this audio, your device is silently screaming out into the void.
It really is.
It's, negotiating with invisible bouncers, translating numerical coordinates on the fly, and relying on, like, pulses of light shooting through glass cables at the bottom of the ocean.
Right, all in a fraction of a millisecond.
Exactly. Just to keep this playback from stuttering, we tend to treat the internet like this ambient utility, like water from a tap,
Yeah, we just expect it to be there.
Right. But beneath that smooth user experience is this chaotic, hyper-coordinated ballet of physical engineering and logical protocols.
I mean, it is a miracle it works at all, let alone with the reliability we expect every single day.
Seriously.
We look at a Wi-Fi icon on our phone and assume a direct, simple connection to a cloud somewhere. But the reality is this massive labyrinth of hardware handoffs, frequency multiplexing, and deeply complex encapsulation protocols.
It's intense.
It is. Every single packet of data has to survive a brutal obstacle course before it ever renders on your screen.
Okay, let's unpack this. Because today's mission for this deep dive is pulling apart the specific mechanics of that obstacle course.
We are getting right into the plumbing today.
We really are. We're digging into the core architecture of network infrastructure, looking specifically at the frameworks laid out in the CompTIA A+ network models.
And, we're not just defining acronyms today.
Right. If you're listening to this, you already know what a router or a local area network is. Today, we are looking under the hood at the how and the why.
Yeah, the actual mechanics.
We're analyzing how a network fundamentally routes traffic at the packet level, the actual physics of the physical mediums bringing that data into your building, and the exact syntax your machines use to prevent total network collision.
So we have to start where the abstract digital world crashes into physical reality.
The hardware.
Exactly. The hardware sitting at the edge of the network. Because, before any routing logic can happen, you have to manage the physical signal itself.
So let's talk about the gateway, the modem. On a surface level, people just think of it as the box that gives them internet.
Right. Sure, the magic internet box.
Right. But structurally, it is performing a highly specific translation between two completely different types of networks.
Think about the physical infrastructure of an internet service provider, your ISP. They are sending data over vast distances.
Right.
And that requires transmitting it as an analog signal. So varying waves of electrical voltage over copper, or radio frequencies over coaxial cable, or even pulses of light over fiber.
But your computer processor can't read an analog wave.
Exactly. It only understands discrete digital binary logic. Zeros and ones, nothing in between.
So the modem...
Which is short for modulator to modulator, by the way.
Oh, right, of course.
Yeah, the modem is the hardware bridge performing that translation in real time. It takes that continuous analog waveform and samples it.
Converting it on the fly.
Converting phase shifts and amplitude changes into a digital bit stream that the local network hardware can actually process.
And once it's translated into a digital bit stream, it's just raw data. Like, it doesn't know where it's going yet.
It needs direction.
Right, it needs the router.
Right.
I always thought about the router as a postal sorting facility.
That's a great way to look at it.
It's not just passing things along. It's actively reading the destination IP addresses on these data packets, right?
Yeah.
And making split-second decisions based on its internal routing tables.
What's fascinating here is the sheer computational overhead required to do that at scale.
Right, because it's happening constantly.
A router is operating at layer 3 of the OSI model, meaning it is physically stripping away the outer physical frame of the data packet, examining the logical IP address inside.
Like opening an envelope.
Exactly. Opening the envelope, checking the address against its routing table to find the best possible path out, rewriting a brand new physical frame for the next leg of the journey, and then pushing it out to the next hop.
And it's doing this thousands of times a second.
Millions in enterprise environments. And our sources delineate the specific roles here. You have LAN routers managing the subnets within a corporate environment.
The local area network.
Right. And then you have WAN routers handling the border, the wide area network connection that actually faces the public internet.
But the router only gets the data to the correct subnet, right? Like the correct neighborhood.
Yes, exactly.
If I have a corporate office with, 50 workstations, 24 printers, and some local file servers, the router isn't physically wired to all of them.
No, that would be a nightmare. That local distribution falls to the switch.
Right. So how does the switch differ from the router in this context?
Well, the switch is operating primarily at layer 2. So unlike an old school hub,
Little hubs. Those were awful.
Yeah, they just blindly repeated a signal out of every single port. It caused massive data collisions. But a modern switch contains specialized hardware.
ASICs, right?
Yep, application-specific integrated circuits. ASICs allow it to manage traffic at wire speed. It maintains something called a MU address table in its memory.
So as devices plug in and start talking on the network, the switch is, like, actively learning which physical hardware address is connected to which specific port.
It is dynamically mapping the entire physical layout of the network.
That's so smart.
It really is. So when workstation A sends a file to printer B, the switch looks at the destination MA address in the frame, checks its table, and forwards that data only down the single wire connected to the printer.
It creates like a private tunnel just for them.
Exactly, a dedicated collision-free microsegment for that one conversation.
Which is brilliant for wired connections. But the moment you introduce smartphones and laptops, you need the access point.
Right.
The AP.
Right, the AP broadcasts that local network out over radio frequencies.
And wrapping all of this up, standing between the local network and the wild west of the public internet, is the firewall.
The enforcer.
Yeah.
The firewall acts as the absolute security enforcement point. Fundamentally, it relies on an ACL, a network access control list.
To dictate what traffic is allowed to pass through,
Yeah,
right?
through the router's interfaces.
You know, the classic analogy is the bouncer with a VIP list. But I think that sells modern firewalls short.
Oh, definitely.
Like a basic stateless firewall just checks the IP address in the port, which is like a bouncer checking your ID.
Right, simple, allowed or denied.
But a modern stateful firewall is more like a hyper-vigilant hotel concierge. It doesn't just check the ID at the door. It remembers the context of the conversation.
Yes, the state of the connection.
Right. If I request a web page from a server, the firewall records that state. When the server tries to send the data back in, the firewall allows it because it remembers I initiated the request.
It knows you asked for it.
Exactly.
Yeah.
But if that server just randomly tried to push data into my network unprompted, the firewall drops it immediately.
That stateful packet inspection is absolutely crucial. And in an enterprise environment, firewalls aren't just facing the outside world.
Oh, really?
No, they are deployed internally to segment departments. Like the engineering department might be physically connected to the same core switch as the HR department. But a firewall sits between those VLANs, ensuring that an engineer's workstation absolutely cannot ping the HR payroll server.
Okay, I want to push back on this hardware layout, though.
Okay, go for it.
We just outlined a stack of 5 distinct devices: the modem, the router, the switch, the access point, and the firewall.
Right.
But if you walk into a typical small business or look at the setup in someone's home, you know, they don't have a rack of 5 separate enterprise appliances.
No, of course not.
They have a single blinking plastic box provided by their ISP, the SOHO router, small office home office unit. By cramming all of those dedicated, computationally heavy tasks into one consumer-grade CPU, there has to be a severe bottleneck.
Oh, the compromise is massive.
It has to be.
A SOHO router is a marvel of integration, don't get me wrong. But it is very much a jack of all trades and master of none.
Right.
When you combine a modem, a routing engine, a 4-port switch, a Wi-Fi radio, and a firewall into a device with, limited RAM and a cheap processor, you inherently limit concurrent connections and overall throughput.
So if you have a household streaming 4K video, downloading huge game updates, and running 2 video conference calls simultaneously.
Which is pretty standard today.
Right. It's not always the internet pipe that's failing, is it?
Yeah.
The SO Reach Router's CPU might literally be maxing out trying to manage the NAT table translations and the firewall states all at once.
That is precisely where the failure point often lies. People blame their ISP, but it's their box suffocating under the load.
Wow.
In an enterprise deployment, you decouple these functions. You use a dedicated hardware firewall appliance from, say, Palo Alto or Fortinet that has custom processors designed purely for deep packet inspection.
Right, taking the load off.
Exactly.
Yeah.
You deploy standalone wireless access points on the ceiling powered via Ethernet, managed by a central controller to seamlessly hand off client devices as people walk through a building. Distributing the computational load is really the only way to achieve true stability at scale.
So we have the local network architecture built out, the traffic management is in place, but the data still has to physically leave the building.
Right. It does. It has to hit the wire.
The modem has to push that analog signal across a physical medium. And when we look at the actual pipes connecting our buildings to the IST, we are largely looking at a massive generational hack of existing infrastructure.
We're talking about the delivery methods here: cable, DSL, and fiber. And your characterization of it as a hack is historically very accurate, particularly for cable and DSL.
Right, they just repurposed what was there.
The telecommunications industry realized they already had millions of miles of copper wire buried underground and strung on telephone poles.
So let's start with cable internet. This utilizes the coaxial cabling originally laid down to deliver cable television.
Yeah, and the physical properties of coaxial cable are actually quite robust.
This is the shielding, right?
Yes, you have a center copper conductor wrapped in an insulating layer, and that's surrounded by a braided metallic shield. That shielding provides excellent protection against electromagnetic interference.
Which allows them to pump a lot of bandwidth through it. The ISPs use the DOCSIS standard, right? Data over Cable Service Interface Specification.
That's the one. They take the vast frequency spectrum available on that coaxial cable, reserve a few channels for legacy television, and basically allocate all the rest to high-speed data.
But the limitation with cable, as I understand it, is that it's a shared medium.
Very much so, at the neighborhood level.
Like the coaxial cable running down your street is a single collision domain, right? Divided among you and your neighbors using time division and frequency division multiplexing.
Exactly. So if everyone in your neighborhood starts downloading massive files simultaneously, say on a Friday night, the total available bandwidth at the local node is saturated.
And everyone slows down. Now compare that to DSL, digital subscriber line. This leverages the public switched telephone network, the PSTN.
The old copper phone lines?
Unshielded, twisted copper lines that were literally designed a century ago to carry the human voice.
But the human voice only requires a very narrow frequency band, roughly 300 to 3400 hertz.
Right.
DSL technology operates by pushing digital data over the much higher, totally unused frequencies on those exact same copper pairs.
So they're sending data on frequencies we can't hear.
Precisely.
But unshielded copper is incredibly susceptible to attenuation and crosstalk, isn't it? The signal degrades rapidly over distance.
Which is the defining constraint of DSL. Your speed is entirely dictated by the physical length of the copper wire between your modem and the ISP's equipment.
The DSLAM, right.
Yes, the digital subscriber line access multiplexer located in their central office.
So distance is everything.
If you live within a few thousand feet of the central office, you can achieve excellent speeds using technologies like VDSL. But if you are a few miles away, the signal attenuation is so severe that your bandwidth drops to an absolute crawl.
And the sources outline two primary implementations here, right? Asymmetrical DSL and symmetrical DSL. Asymmetrical gives you a wide pipe for downloading and a tiny straw for uploading.
Because the ISP engineers know that the average residential user consumes far more data than they produce. We watch movies, we don't host servers.
Right, so they allocate more of the available frequency spectrum to the downstream traffic.
Exactly. But a business running, say, an on-premise web server or constantly syncing massive databases to the cloud, they cannot survive on a narrow upload channel.
So they use symmetrical DSL.
Right, which provisions the frequency bands equally, ensuring the upstream and downstream speeds actually match.
But eventually, copper simply hits the laws of physics.
It does. It has a hard limit.
You can only push so much electrical voltage over a wire before interference makes the signal unreadable. And that brings us to fiber optics.
Well, holy grail.
Moving away from electrical pulses entirely and transmitting data using photons. Literally pulses of light shooting through strands of glass thinner than a human hair.
The jump from copper to fiber is a total paradigm shift. Fiber optic cables utilize the principle of total internal reflection.
Okay, break that down for us.
So the core of the glass fiber has a slightly higher refractive index than the cladding around it, meaning the light wave continuously bounces off the boundary, traveling for miles with almost zero signal degradation.
Wow.
And complete immunity to electromagnetic interference.
I mean, you can run a fiber cable right next to a massive industrial power generator, and the data won't even flinch.
It won't even notice it's there.
But digging up every street and yard in a country to lay new glass is astronomically expensive. So ISPs use different rollout strategies.
Right.
We have this alphabet soup in the sources of FTTN, FTTC, FTTP, and FTTN.
Yeah, it all comes down to where the fiber stops and the old copper network begins.
Right.
Let's start with FTTN, fiber to the node. The ISP runs a high-capacity fiber optic line to a central neighborhood node. But from that node to your house, they use the existing legacy copper telephone line.
So you have this massive lightning-fast optical highway that suddenly dumps all its traffic onto a tiny congested dirt road for the last mile.
That's exactly it. And because that last leg relies on copper, it suffers from all the distance limitations we just discussed with DSL.
Right, of course. So what's the next step up?
The next step is FTTC, fiber to the curb, or cabinet.
Okay, so this pushes the fiber much deeper into the neighborhood.
Yes. The optical cable runs to a telecommunications cabinet sitting right on your street corner. So the copper run to your front door might only be a few hundred feet.
And that short copper run allows for advanced technologies, right? Like VDSL2 vectoring.
Yeah, which uses complex phase shifting to cancel out crosstalk between the copper wires, drastically increasing the speed.
But again, as the source is warm, the local cabinet is still a shared bottleneck. At peak hours, that short copper loop can still struggle if the cabinet's backhaul isn't provisioned correctly.
Exactly, which is why the ultimate goal, the gold standard, is FTTP, fiber to the premises, or FTTH, fiber to the home.
This completely eliminates the copper bottleneck.
Entirely. A dedicated optical fiber runs directly from the ISP's facility into an optical network terminal attached to the side of your actual house.
And the bandwidth potential there is staggering.
Oh, it's immense. They often utilize wavelength division multiplexing, where different data streams are transmitted simultaneously over the same single strand of glass by using different colors or wavelength of laser light.
That's just incredible. But what if you are physically isolated, like a farm in the mountains, a research station, or even a historic building in the city center, where zoning laws prohibit drilling for new cables?
Then you have to turn to wireless alternatives, fixed wireless and satellite.
Okay, let's talk fixed wireless first.
For remote terrestrial locations, wireless internet service providers, or WISPs, they mount a highly directional parabolic antenna on the customer's roof and point it at a local radio tower.
So it provides a dedicated point-to-point microwave link.
Right. But if you don't even have line of sight to a local tower, you have to look up.
Satellite internet. And the sources delineate between geostationary and low Earth orbit systems.
Geostationary satellites orbit at roughly 22,000 miles above the equator. They match the Earth's rotation perfectly.
So to a dish on the ground, the satellite appears perfectly still in the sky.
Yes. And this provides massive, continent-wide coverage areas from a single satellite.
But the latency is brutal, isn't it?
It is punishing. Even at the speed of light, an electromagnetic wave takes a noticeable amount of time to travel 22,000 miles up to space, get processed, travel 22,000 miles back down to a ground station, route to a server, and then do the entire 44,000-mile round trip again just to acknowledge the packet.
So you're looking at latency well over, 600 milliseconds?
At least, which is fine for downloading a large file in the background, but utterly disastrous for a real-time voice call.
Right.
Or a VPN connection that relies on rapid acknowledgement.
Which is exactly why the industry is shifting aggressively toward LEO, low Earth orbit constellations like Starlink.
Right. LEO's satellites orbit much closer, typically between 300 and 1,200 miles up.
That's a huge difference.
It is. The distance penalty is virtually eliminated, bringing latency down to terrestrial levels. But because they are so close to the Earth, their coverage footprint is very small, and they orbit the globe incredibly rapidly.
So how does the dish stay connected?
Well, to maintain a connection, the user's dish has to utilize an electronically steered phased array antenna.
Meaning no moving parts, just steering the beam electronically.
Exactly. It tracks a satellite moving across the sky, hands off the connection to the next satellite as it rises over the horizon, and does this continuously without dropping packets.
It's just wild that this works seamlessly. And finally, the wireless pipe that we all use constantly. Cellular radio, the evolution from 3G to 4G LTE, and now 5G.
The cellular evolution is really a story of spectral efficiency. 3G brought us rudimentary data. 4G long-term evolution moved cellular networks to a fully IP-based packet-switched architecture, which finally gave us enough bandwidth for sustained video streaming.
But the transition to 5G isn't just about making the radios a little more powerful, right? It requires a fundamentally different deployment strategy.
Totally different.
The sources emphasize the complexity of the 5G rollout, specifically the reliance on massive multiple input, multiple output, or MEO technology.
Yeah, 5G networks, especially those utilizing high-frequency millimeter wave bands, have incredible bandwidth, but terrible penetration.
Right, like a millimeter wave signal can be blocked by thick foliage, rain, or a brick wall.
Easily. So instead of putting one giant high-powered cell tower in the middle of a town, network engineers have to deploy dozens or hundreds of microcells on streetlights and buildings.
And the MEO antennas use beamforming, don't they?
Yes, which is amazing tech.
So instead of broadcasting radio waves in a giant omnidirectional circle like a sprinkler, the antenna array calculates the exact physical location of your smartphone and shoots a concentrated phased beam of radio energy directly at you.
Tracking you as you walk down the street. It is an astonishing feat of spatial multiplexing. It allows the tower to reuse the exact same frequency for dozens of different users simultaneously, simply by pointing the beams in different physical directions.
So we have the physical architecture. The copper, the glass, the radio waves. We have millions of miles of cabling and billions of devices constantly transmitted.
It's a lot of noise.
Right. And the central engineering problem of the internet is this. How does a tiny packet of data originating from a server in Tokyo navigate this chaotic global web of hardware to arrive at your specific smartphone in Chicago out of the billions of devices currently turned on?
That requires a rigid, universally understood addressing protocol, the language of the network. We were moving from the physical layer 1 and layer 2 up to the logical routing of layer 3.
IPv4 versus IPv6.
Exactly.
Let's examine the foundational architecture first. IPv4, Internet Protocol version 4, created in the early days of the ARPANET, and it's a 32-bit addressing system.
Right, and a 32-bit system means the absolute mathematical maximum number of unique addresses available is 2 to the power of 32, which is roughly 4.3 billion.
And to make those 32 bits readable for humans, we write them in dotted decimal notation, 4 octets, like 192.168.1.1.
But the computer only sees the binary string of zeros and ones. That dotted decimal format is purely an abstraction layer to prevent network administrators from losing their minds when configuring interfaces.
Makes sense.
But an IPv4 address isn't just a random serial number. It has an internal structure. It is divided into 2 distinct components, the network ID and the host ID.
So it's hierarchical. The network ID is the macro location, right? The specific subnet or corporate network the device belongs to.
Yep.
And the host ID is the micro location, the specific machine on that subnet. But looking at an IP address like 1050.2.1 you can't inherently tell where the network part ends and the host part begins.
No, you need a cipher to decode it, and that is the subnet mask. The subnet mask is another 32-bit number, often written in slash notation like 24, or in dotted decimal like 255.255.255.0.
So when a router receives a packet, it looks at the destination IP and it looks at the subnet mask.
And it performs a bitwise A&D operation.
Okay, let's walk through that.
The router compares the IP address and the subnet mask at the binary level. Wherever the subnet mask has a binary 1, that part of the IP address is locked in as the network ID. Wherever the subnet mask has a binary 0, that is the host ID.
So this mathematical operation allows the router to instantly isolate the network destination, check its routing table for the next hop, and fire the packet out the correct interface.
Without caring about the specific host until the packet actually reaches the destination subnet.
It's incredibly efficient routing logic. But IPv4 has a catastrophic flaw that became apparent by the late 1990s.
We ran out of numbers.
Right. 4.3 billion addresses sounds like a lot until you realize the global population is 8 billion. And today, an average user has a laptop, a smartphone, a smartwatch, a smart TV, and internet-connected light bulbs. We mathematically exhausted the IPv4 pool.
So the industry deployed temporary band-aids to survive. They introduced private IP addressing ranges.
Like the 192.168 networks.
Exactly. The 192.168, the 172.16, the 10 dot whatever networks. These are addresses that are non-routable on the public internet.
So millions of households can reuse the exact same 192.168.1.5 address on their local LAN.
Yes, and they rely on the router-performing network address translation, NAT, to dynamically map all those private internal addresses to a single, public, externally routable IPv4 address provided by the ISP.
NAT saved the internet from total collapse.
It did, but it broke the fundamental end-to-end connectivity model the internet was actually built on.
The permanent solution outlined in the CompTIA A material is IPv6.
Right, and IPv6 fundamentally solves the exhaustion crisis by expanding the address space from 32 bits to 128 bits. The increase isn't just linear, it's exponential.
So how many addresses is that?
2 to the power of 128 provides 340 undecillion addresses.
It is a number so large it loses meaning. Trillions of addresses for every square inch of the Earth's surface. We could assign a public IP address to every single blade of grass on the planet and not even dent the pool.
It's practically infinite.
But because the addresses are 128 bits long, the notation is entirely different.
Right. We abandon dotted decimal and use hexadecimal characters separated by colons. 8 groups of 4 hexadecimal digits. For example, 2001 .0db8, .853, .a2e, .037, .7334.
The thought of a human typing that in without making a typo is terrifying.
Which is why IPv6 includes rules for compression. You can drop leading zeros in any group, and if you have contiguous groups of all zeros, you can replace them entirely with the double colon.
Oh, that helps.
Yeah. But the structural logic remains similar to IPv4. The first 64 bits typically act as the network prefix provided by the ISP, and the last 64 bits act as the interface ID, uniquely identifying the host.
The sources highlight that IPv6 isn't just about infinite addresses, though. It introduces different types of addresses. We have a global unicast address, which is your public, globally routable address, but then there is the link local address.
Link local is a brilliant mechanism. In IPv4, if a device doesn't have an address, it's essentially crippled. In IPv6, the moment you turn a network interface on, it automatically generates its own link local address, using the prefix v80.delo combined with its own MASE address.
Wait, really? So without needing a router, without needing any external configuration, the device instantly gives itself an identity so it can communicate with other devices on the exact same local physical link?
Yes. It uses the Neighbor Discovery Protocol, utilizing ICMPv6 messaging, to ensure no other device on the link is using that same address, and then it joins the local network.
That's so cool.
Now, a link local address can never be routed out to the public internet, but it is essential for local network management and routing protocol neighbor adjacencies.
The security architecture is also completely revamped, right? Because in IPv4, IPsec, the suite of protocols that encrypts and authenticates data at the network layer, was an afterthought. It was bolted on later.
Which is why configuring VPNs in IPv4 can be incredibly complex.
Right. But in IPv6, IPsec support is baked directly into the protocol standard.
If we connect this to the bigger picture, the transition from IPv4 to IPv6 is a massive logistical hurdle. You have billions of legacy IPv4 devices and routers worldwide. You cannot schedule a flash cut where everyone reboots on a Tuesday and suddenly speaks IPv6.
Which brings us to the transition mechanism, dual stack.
Exactly. Dual stack involves running both the IPv4 and IPv6 protocols simultaneously on the same network interfaces and routers.
So a modern operating system will request both an IPv4 and an IPv6 address.
Yes. When an application initiates a connection, the OS prefers the IPv6 path if it's available end-to-end. If not, it seamlessly falls back to IPv4. It allows for a gradual, decades-long migration without breaking legacy connectivity.
Okay, let's step back and look at the user experience here. We just established that navigating the internet requires managing 32-bit binary strings or 128-bit hexadecimal arrays.
Right.
If users actually had to interface with the network at that level, the internet would only be used by academics and engineers. The only reason modern commerce and social media function is because we abstracted that complexity away.
The entire system relies on automation. The network configuration saviors, DNS and DHCP. Without these two application layer protocols, the network infrastructure we just discussed is practically unusable for the average human.
So let's tackle the translation engine first. DNS, the domain name system. The problem is simple. Humans remember words, but routers only route numbers.
When you open a browser and type a URL like google.com, your computer has absolutely no idea how to reach that destination because there is no IP address attached to it. The computer must pause the connection attempt and perform a DNS lookup.
It queries a DNS server asking, what is the A record, the IPv4 address, or the quad A record, the IPv6 address for this specific host name?
And the DNS architecture is a globally distributed hierarchical database.
So it's not just one server with all the answers.
Far from it. Your computer first checks its local cache. If it doesn't know the answer, it asks the local DNS server, usually provided by your ISP. If that server doesn't know, queries the root servers, which direct it to the top-level domain servers.
Like the servers managing all .com addresses.
Right, which finally point to the authoritative name server for that specific domain. The IP address is returned, cached locally to speed up future requests, and the browser finally initiates the TCP connection.
And this all happens in milliseconds. But DNS only works if your computer actually has an IP address of its own to send the request from.
That's the catch.
Right. And when you walk into a coffee shop, open your laptop, and click the Wi-Fi network, your computer starts with nothing.
That is where DHCP, the Dynamic Host Configuration Protocol, takes over. In the early days of networking, an administrator had to physically walk to a machine, open the network adapter settings, and statically type in an IP address, a subnet mask, a default gateway, and a DNS server.
So tedious.
And if they made a typo or accidentally assigned an IP that another machine was already using, it caused an IP conflict and the network crashed.
So DHCP automates that entire provisioning process, and it does it using a four-step sequence known as the DORA process, D-O-R-A. Discover, offer, request, acknowledge. Let's look at the packet-level mechanics of DORA.
Step 1, discover. The client device connects to the network but has no IP address, so it constructs a DHCP discover packet. Because it doesn't know the IP address of the DHCP server, it sets the destination IP to 255.255.255.255.255.
Which is the universal broadcast address.
And it sets the destination MAC address to all Fs.
So it is literally shouting across the entire Layer 2 broadcast domain, asking, is there a DHCP server listening?
It really is shouting. The switch floods that broadcast frame out of every single port. The router, acting as the DHCP server, receives the broadcast, examines it, and moves to step 2, the offer.
Yeah.
The server looks at its address pool, selects an available IP address, reserves it temporarily, and sends a DHCP offer unicast back to the client's MAC address, essentially saying, I am an authorized server, and I can lease you this specific IP address.
Okay, step 3, request. The client might receive multiple offers if there are redundant DHCP servers on the network. It selects one, usually the fastest response, and broadcasts a DHCP request packet.
And this broadcast serves two purposes, actually.
Oh, really?
Yeah. It tells the chosen server, I accept your offer, and it simultaneously tells any other listening servers, I've accepted an offer elsewhere, you can release the IPs you reserved for me.
That is so elegant. Finally, step 4, acknowledge. The DHCP server commits the IP address to its database, binding it to the client's MAC address for a specific lease duration, and sends a DHCP acknowledge packet containing the IP address, the subnet mask, the default gateway, and the DNS server addresses.
And boom, the client applies the configuration and is now fully operational on the network.
So what does this all mean for the listener? Imagine an alternate reality where every time you went to a coffee shop, you had to manually type in a 12-digit number just to get your phone to connect to the router.
It would be unusable. The sheer elegance of that process happening in the background every time we connect to a network is incredible.
But what happens when it fails? If the DHCP server crashes or the scope of available IP addresses is exhausted, a Windows machine doesn't just sit there silently.
No, it initiates a fallback mechanism.
Right, it falls back to APPA, automatic private IP addressing.
If a device sends out DHCP discover broadcasts and receives no offer after a certain timeout period, the operating system self-assigns an IP address from a very specific reserved range.
The 169.254.0.0.254.255.255 range.
Yes, and before it actually assigns it, it uses ARP, the Address Resolution Protocol, to probe the local network and ensure no one else happens to have self-assigned that exact same 169.254 address.
That's a good safety check.
Yeah, once it verifies the address is clear, it applies it with a 16 subnet mask.
This is a huge troubleshooting flag. If I get called to a desk because someone has no internet, and I run an ipconfig command and see an IPv4 address starting with 169.254, I instantly know the problem isn't the physical cable or the DNS server.
Right, you know immediately.
The problem is that the DORA process failed, and the device couldn't reach the DHCP server.
And the crucial limitation of API-PA is that it does not configure a default gateway.
Right.
A device with a 169.254 address can ping and communicate with other devices on the same local switch that also have APA addresses. They can share files locally. But because there is no default gateway, they have absolutely no way to route traffic off the local subnet. They cannot reach the internet.
So we have the physical infrastructure, the logical IP addressing, and the automated configuration protocols working in perfect harmony. The final dimension to explore from the CompTIA A+ architecture is the actual behavior of the data payload as it traverses this environment.
The rules of communication.
Right. We're looking at the transport layer of the TCP IP stack. IP addressing gets the packet to the correct destination hardware. But once the packet arrives at the server, how does the server know what application is supposed to process the data? Is it an email? Is it a web page request? Is it a file transfer?
That differentiation is handled by ports. A port is a 16-bit logical construct, meaning there are 65,535 possible ports on any given IP address.
So if the IP address is the street address of an apartment building, the port number is the specific apartment door.
Perfect analogy. The operating system binds specific applications to specific ports, creating a socket. So an IP address plus a port number. The CompTIA A material mandates understanding the well-known ports, the standardized doors used by universal services.
Let's decode the common traffic patterns on a network. Unencrypted web traffic, HTTP, defaults to port 80. But almost all web traffic today uses HTTPS, utilizing TLS encryption, which communicates over port 443.
File transfer protocols rely on different ports. Legacy FTP utilizes port 20 for data transfer and port 21 for control signals.
But nobody really uses legacy FTP anymore, do they?
Not if they want to be secure. A secure FTP operating over an encrypted SSH tunnel uses port 22.
Email routing is highly segmented as well. To send an email from your client to a server or for servers to route mail between each other, the network uses SMTP on port 25.
But retrieving that email uses different protocols. The older POP3 protocol downloads the email and deletes it from the server using port 110. Modern IAMAT, which synchronizes the mailbox state across multiple devices, utilizes port 143, or the secure version on port 993.
And the back-end infrastructure protocols we discussed also have dedicated ports. DNS hostname resolution queries operate on port 53. The DHCP broadcast process utilizes ports 67 and 68.
And for network administration, you frequently see Remote Desktop Protocol, RDP, on port 3389, allowing full graphical control of a remote machine. And for monitoring the health and bandwidth of switches and routers, the Simple Network Management Protocol, SNMP, pulls devices on ports 161 and 162.
But the port number only identifies the application. It doesn't dictate how the data stream is fundamentally managed during transit. At the transport layer, the network uses two radically different protocols to encapsulate the data.
TCP and UDP.
Right. TCP, the transmission control protocol, and UDP, the user datagram protocol. The decision of which to use dictates the reliability, the speed, and the overhead of the communication.
Let's dissect TCP first. It is connection-oriented. It prioritizes absolute accuracy over raw speed.
So, before a single byte of application data is sent, TCP establishes a formal session using a three-way handshake. The client sends a SYN packet, a synchronized packet. The server acknowledges the request and synchronizes its own sequence numbers by sending back a SYN ACK.
And finally, the client sends an ACK, an acknowledgement.
The connection state is now established.
Right. And as the data flows, TCP meticulously numbers every single segment. It utilizes a sliding window protocol to manage flow control. If the receiving server is getting overwhelmed, it can shrink the window size, basically telling the sender to slow down the transmission rate.
The defining feature of TCP is guaranteed delivery. When the sender transmits a segment of data, it starts a timer.
And if it does not receive an explicit acknowledgement from the receiver before the timer expires, TCP assumes the packet was lost in transit and automatically retransmits it.
It's like sending a registered letter with the return receipt requested. You know they got it.
Exactly. It is a phenomenal system for data integrity. If you are downloading an encrypted financial database or an executable software update, a single missing bit of data corrupts the entire file. TCP ensures perfect ordered delivery.
But that reliability comes with massive overhead. The handshake, the constant acknowledgments, the sequence tracking it adds a lot of latency.
Which brings us to UDP, the User Datagram Protocol. UDP is entirely stateless and connectionless. It strips away all the reliability mechanisms of TCP.
There is no three-way handshake. There are no sequence numbers. There is no flow control. And crucially, there are no acknowledgments. It's like throwing a postcard out the window of a moving car toward a mailbox. It's faster, but you just have to hope it gets there.
UDP encapsulates the application data into a datagram, slaps the destination IP and port on the header, and fires it into the network. It provides best effort delivery. If a router along the path becomes congested and drops the UDP packet, it is gone forever.
The sender doesn't know it was dropped and the receiver doesn't know it's supposed to arrive.
This raises an important question, though. Why would any engineer choose to use a protocol that inherently allows data loss?
Right, that sounds terrible.
But for specific real-time applications, speed is critical, and late data is entirely useless data. Consider a voice-over IP phone call, or a live video stream, or a fast-paced multiplayer video game.
These applications generate continuous streams of time-sensitive data.
Exactly. If we force a real-time voice call to use TCP, and a packet containing 20 milliseconds of audio was dropped by a congested router in Chicago, the TCP protocol would halt the entire data stream. It would wait for the timeout, request a retransmission, wait for the packet to be resent, and then try to play it back.
From the user's perspective, the phone call would constantly freeze, buffer, and stutter in an attempt to perfectly recreate the audio stream. It would render real-time communication impossible.
But by using UDP, the application accepts the loss. If that 20-millisecond audio packet is dropped, UDP simply ignores it and plays the next packet that arrives.
The user might hear a nearly imperceptible pop in the audio, but the conversation flows without interruption. For streaming and gaming, dropping a frame is vastly preferable to lagging the entire system, waiting for an acknowledgement.
DNS queries are another prime example of UDP efficiency. A DNS request is typically a tiny single-packet query and a single-packet response. Setting up a full TCP three-way handshake just to ask for an IP address would triple the network traffic and drastically slow down web browsing.
UDP allows for rapid, lightweight transactions.
It really does.
We've traced the entire architecture from the physical cables in the street all the way up to the application sockets. The mechanics of the CompTIA A plus networking models reveal an environment of staggering complexity. We've dissected the multiplexing of fiber optics, the bitwise logic of subnet masking, the automated lifelines of DHCP, and the rigid flow control of the TCP/IP stack.
The architecture is a testament to iterative engineering. I mean, we have protocols designed in the 1970s operating seamlessly alongside gigabit photonics and phased array millimeter wave antennas.
So the next time you, the listener, click a link and a web page loads instantly, consider the invisible gauntlet that data just ran. It was modulated into digital frames, routed through M-key tables by ASICs, shot across oceanic fiber lines, translated by NAT, verified by stateful packet inspection, and acknowledged via TCP windowing, all in a fraction of a second.
It is the hidden infrastructure that holds the modern world together.
It really is.
And the architecture is not static. If we extrapolate the current trends we analyzed, the sheer bandwidth and spatial multiplexing of 5G MIMO networks, combined with the infinite globally routable address space of IPv6, we are approaching a fascinating inflection point in network topology.
What do you mean?
We may be moving toward a reality where the concept of the local area network, the private subnet shielded by a NAT router in your house, becomes completely obsolete. If every single sensor, appliance, and computing device possesses its own permanent IPv6 address and connects directly to the internet backbone via cellular edge computing, well, the traditional hardware router sitting on your desk might soon be viewed as a relic of a transitional era in networking.